set theory. So set theory is what we are first looking at. So in order to build up our understanding of sets, we first define what a set is. So a set, what is a set? So a set is a well-defined collection of objects called what? Elements. Well-defined collection of objects called elements. So we call these objects, a well collection of these objects, we call them what? Elements or members of that set. That is the definition of a set. So we have a lot of what is sets, examples of sets we can give. As long as it's a well defined collection, it can be a set of fruits, meaning you have fruits in that set. You expect to have what? Fruits in the set. Set of vehicles, you expect what? Vehicles in that set. So but in this course, because we are looking at numbers and real analysis, from the word itself begins a build up on the study of real numbers. So now we have things or examples of sets of numbers. So e.g. sets of numbers that we have, we have sets of natural numbers. Set of natural numbers. So this set includes the numbers that we of course we use when counting one, two, three, all the way up to what? Infinity, like that. So these are natural numbers. Then we have the set of integers. So the set of integers, that is both positive and negative what? Integers. Positive, negative what? Integers. So we know it goes, yeah, it's infinity that way, like negative, and all that way. These are what? Integers, like that. So the set of integers, those are integers. Then we have rational numbers. So rational numbers, by definition, are just numbers that can be expressed in the form a over b, where b is not equal to 0, and a and b are not common, have no common factors. So a and b have no common factors. So that's what rational versus numbers are. Then irrational numbers. So irrational numbers are just the opposite of what? Rational numbers. These cannot be expressed in the form what? A over b. So these cannot be expressed in this form. Can't be expressed in this form a over what? Over b. So these are just basic sets of what? Of numbers. Then we have other other numbers that which we have, like set set of algebraic numbers. Sure, maybe these are new to you. So we have set of algebraic, so algebraic numbers. Okay, these are denoted as these are just denoted with letter a, like this. So these are algebraic numbers. So these are solutions to what? To polynomial functions or equations, polynomial functions or equations, I mean. So these are algebraic numbers. So, and you have transcendental numbers. Transcendental numbers. So the transcendental numbers, this is where you find numbers like pi, uh, maybe, yeah, pi, the this e, yeah, and all those. These are transcendental numbers. So these are other forms of numbers, though they are not really of that importance. You just have to know them. Yeah, but we won't use them in this course. We will definitely focus on what the first four we talked of including the complex numbers. So as we know how it goes, it's the natural numbers being a subset of the integers, being a subset of the rationals, which are a subset of real numbers, and these real numbers are a subset the complex what numbers. So this is how it goes, and we will talk of these mostly in this course. So now uh, we'll build up from there. So in this course, when we shall denote, since we're looking at sets, we shall denote sets. So a set will be denoted by what? By an uppercase letter or a capital letter. So for example, x, this is a set. So maybe x is a set of vowels, that is r, a, e, and o and u there. So this is a set. Then as you can see inside, we have the what? The elements or the members. So the members shall be denoted by what? By lowercase letters. Members by lowercase letters. So now we we shall say that, for example, we can see here that you can see that A is part of this set X. So how do we say that A is what? Is a member of set X? So we will say that, say A is a member. So this symbol here will stand for or will mean a member of set X. I'm sure we already know that. And if it's not, for example, B here is not, so B is not a member of set X, like that. That's the denote. That's how we will denote what sets. Now let's carry on from here. So uh, so as I say, that definitions are very important to this course. So if, or we say let, so we must learn the language that is used in this course. So we have a mathematical language, of course. So let x and y be non-empty sets. Be non-empty sets, meaning that these two sets, x and y, have something in them. They are not what? They are not empty. Yeah. So to denote that, I can say x and y are not equal to the empty what set. So they are not empty. So if we can let these sets be like that, then uh, x, then x is said to be a subset, of y, if, so if every member of x is a member of what? Of y, then x is said to be a subset of y. So if every member of this set x is contained in that set y, then x is a subset of y, denoted as x. So this symbol here is for subset. Okay, like that. So by conversion, we know that the empty set is a subset of what? Every set. Subset of every set. The empty set is a subset of every set, like that. Now let us continue with our definitions. So the next definition is of a proper subset. The next definition is of a proper subset. So uh, we say if every member of x, so if we have, remember those two, we said x and y be non-empty set. So if every member of the set x is a member of what? Of the set y, every member of the set x is also a member of the set what? Y. If this, every member of x is a member of y, but there are members of y that are not in what? In x. So there are members of y contained here we have members in here. Those members, we have some members in y that are not in what? In x. So the first, follow this carefully. The first thing is that everything in what is every member of x is a member of y, but not every member of what y is a member of what x. Then we say that x is a proper subset of y. Proper subset set of y. Okay, so that's that definition there, which is also still denoted in the same way with x, this subset of y. The next thing is, so when we are not sure whether there are some elements of y not in x. So here we are sure that there are some elements of what? In the first part, we're not defining the proper subset. There are some elements in y which are not in x. But now if we're not sure if whether there are some elements of what? Of x, of y, I mean, of y not in x, then we write it like this. So that's if we are not sure, like that. Okay, so that's how we denote that. So we move on to the next definition that we have. So the definition is the next definition that we have is when are two sets what? Equal. When are two sets said to be equal? So two sets are said to be equal. So we are still using, so if we have so we say let a and b be two sets, non-empty sets, of course. They're non-empty, meaning there's something in both of them. So if we say that these two sets a and b are equal, we say a is equal to b if and only if, so when you see this if this stands for if and only if. Okay, so they would write it like that, or they would write the full statement if and only if. So an if and only if statement means that it is true going this way, and the opposite as well going that way is what is true. So a is equal to b and b is equal to a if and only if a is a subset of b, and the backwards being true, that b is also what? A subset of the set a. So this is when two sets are equal. All right, are there any questions up to this point? Okay, the silence. Any questions? All right, so uh, the next thing that we're going to do is have a recap. I understand in first year you did the De Morgan's what laws. So now if we have two sets a and b, two sets a and b, so then uh, the identity a union b complement equal to a intersect b complement, so it's true. So now we're going to what? Prove this. So we're going to prove this. So this is going to be useful uh, as we will go on further. So uh, in first year you look at this where you just deal with two sets, having two sets a and b, of which we do a recap on that. But as we build on further and as we look at uh, indexed family of sets, we will see that we can write this for many sets, many sets. So we will first look at a recap on this. What do we do, or how do we find that? All right, so we find that in the following. So to prove this, the proof is Okay, so we say so this we can only say, as we say, two sets are equal if and only if this part is a subset of the other set. So that's what we must show. So proof. All right. So proof is, we say let X be a member. So as we say, that will be for member of A union B complement. So we say that about this. So we say X be a member of A union B complement. Right. So if it's in the complement of A union B, then it implies X is not a member of what? Is not a member of A union B. A X is not a member of A union B. If it's in the complement, then it's not a member of A union B. Okay. Then in turn, and it means that X is not a member of A, and X is also not a member of what? B. So X is not a member of A, X is not a member of what? Of B. Since it's not in what? In A union B. So we know that A union B comprises of bringing all elements that are in A together with those in what? In B. So if it's not in this, meaning it's in none of them, meaning it's not in A, then it's not also in what? In B, as we have what? Written there. So this means that, so if it's not in A, meaning X then is a member of A complement, since it's not in that set A, meaning it's in what? A complement, and X is a member of what? B complement. So if X is in what? Is, so here, if since it's not in A and it's not in B, then it belongs to A complement and B complement. And if X is in both of these sets, it's in both of what? These sets, means that X is what? Is in, so this means that X is a member of A complement intersect B complement, because we see that now X here becomes the what? The common, the intersection here. So that's why here we even have what? Intersection. So X is a member of A intersect B. So then this will say, or shows the first part to say that A union B complement is a subset of A complement intersect B complement. So we can label that to be our part 1, like that. So we've shown that it is a what? We've shown that this part is a subset of this. So we must show even the reverse. Must show the reverse. So my space here is small. I'll erase this first part of the proof. Then we do the what? The second part of the proof to show that the reverse also is true. Since that's when we know that a set is that a set are equal, or sets are equal when they're subsets in both ways. So conversely, you now come in with this word conversely, meaning when we do the reverse. Conversely, suppose that X is a member of A complement intersect B complement. So we start from this side here. So now if that's a member of that, then if it's in there, if X is in the intersection, meaning that X is a member of what? Of A complement, and X is a member of B complement, since it's in the intersection, meaning it belongs to what? Both sets, meaning it belongs to both sets. Then we have that from here we can move to say, then if it's in the complement, then we know that x, if it's in a member of the complement, meaning that x will not be in the set what, in the set A, since it's in the what, in the complement, and x will also not be in the set what, B. So if that is true, then from there we know that even when we bring these two sets together, if we unite these two sets together, it means that x will still not be a member of the union A union B. So if it's not a member of A union B, meaning x has to be in the what, has to be a member of A union B complement. So this then shows us the second part. So this shows us that A complement intersect B complement is a subset of A union B complement. So you can name this two like that. Right. So from here you just now then make and draw your conclusion. So your conclusion will just be, okay, your conclusion is going to be, you just say combining, since we were naming them, say combining, okay, combining 1 and 2, we have that A union B complement is equal to A complement intersect B complement. So combining the two, A1 and 2, you have that A complement intersect, so you have that A union B complement is equal to A intersect A complement intersect B complement. So that is the end of what, of this proof. So you're done with your proof there. Others would would indicate by writing this box to say the proof is done, or you can write QED to indicate that proof is what, is done. Yeah, or just leave it like that, so we would know that the proof is what, is done. So if you want, you can write that box. I think for me, prefer the box like that, then you know that the proof is done from here. All right, so any questions on this proving? So you can do the other one. So the other one is easy. So it's the same thing. It's A intersect B complement, then you prove that this is equal to uh, A complement union B complement. So yeah, you can prove that. All right, presume there are no questions here, so we move on. uh, the next part, we are going to look at relative we're going to look at relative complement. So in first year relative complement, we understand that it's just the difference between two sets. So talking of relative complement, okay, this is a E complement. So relative complement is just the difference between two sets. So if you have set A and B, so the difference between the two sets, which is A minus B in this case, we will say equal to, so we have that x, such that x is a member of, so x has to be a member of A, and x is not a member of what, of B. So this is what relative complement is. Or even the opposite, you can have like this, where you say now set over x such that x is a member of B and x is not a member of A. Okay, so this same relative complement at times is written in the form A intersect B complement, like that. It is written in that form. So examples on this, examples of relative complement, just to see it in play, is right. So we have that Q. So these rational numbers minus the irrational numbers. Uh, what do you get? What set is this? What set is that? So we're dealing with numbers. So think in terms of numbers. What group of numbers is going to be this? So in short, it's like you're saying you have rational numbers, then you remove irrational numbers from those rational numbers. What do you remain with? Hello? Hello? Am I alone? Alright, so what you remain with here uh, when you remove irrational numbers from rational numbers, so you still remain with what? The rational numbers. So rational numbers, as we know, they can be expressed in the form a over b. These cannot. So meaning these are not even part of the what? The rational numbers. So if you remove the rational from the rational, you still remain with the rational numbers. Then when we remove rational, this set difference, we still remain with what? The irrational numbers, like that. Then we have real numbers. So real numbers, we remove the what? The rational numbers. So if we remove the rational numbers, those that can be expressed in the form of a b. So real numbers, those numbers on a number line. Let's just use that. Now for now, we'll define it like that. But as we go on further in the course, we'll come up with a better way, very well constructed way of defining what these real numbers. So you have them going this way, and these real numbers, we know that they, since we know that they are formed from a number of what? Numbers, number of numbers, that is the rational numbers, and the rational numbers like combined together would form what? Real numbers. So somebody can talk of integers. Integers are also can be expressed in the form of a over b. We know that. So when you remove uh, rational numbers from the real numbers, you just remain with irrational what? Numbers, like that. Then when it comes to removing, so when you remove the irrational numbers, you remain with the rational numbers, like that. So what of when we remove rational numbers from rational numbers? So this, we remove that, we remain with the empty set. So it will be empty because you removed everything there. Then also when we do the same with irrational, it just gives us equal to the empty set. So this is about, or examples of those of how relative complement is in play. All right, we move on to the last part for today's discussion. Yeah, the last part for today's discussion, we look at symmetric difference. So symmetric difference of two sets. So let's say we have two sets x and y. Then the symmetric difference, denoted like this, with an inverted triangle like that, is defined to be x, so difference of y union y difference x. So this is how you get the symmetric what difference. So we can use the examples that were of the same groups of numbers we're having. So if we say the symmetric difference of the rational numbers and the irrational numbers like this, what do we get? So we write it the way we have. So the first part you write here, so those the rational, then you are doing a difference with the irrational, then union here irrational, then you remove all the rationals like that. So what do you get there? So what you get is when you remove the when you remove irrational numbers from the rational ones, you still remain with, since those are not contained in there, so you still remain with the rational numbers. Then your union what? So when you do the second part, you have irrational numbers. So you have irrational numbers. Just alright. So you have irrational numbers. So the union of these forms the real numbers. This forms the real numbers. Okay. So let's erase. So keep the definition. Alright. So uh, the next part, or the next example, we just do if we have symmetric difference between real numbers and the rational numbers. So this will be rational, remove the, oh, I mean real numbers, remove the rational, then union the rational, remove the real numbers. So what are you going to get when you do that? So the first part here, what you're getting when you remove the rational numbers from the real numbers, you get irrational numbers that are going to remain. So you have irrational numbers there. Then this one here, when we remove real numbers from this, so uh, this cannot be contained in this, so we cannot per se remove that there. So this will just what remain empty when this is what is done, or when you find the set difference there, it will remain what empty. So that will be union the empty set, union the empty set. So then this will just give us, so any set union the empty set gives us that set, which is going to be set of irrational numbers. Then we can do this with set symmetric difference with irrational numbers, and we get that the real numbers as minus irrational union irrational uh, and as the real numbers. So there, what are we going to get? So from there we get, when we remove the irrational numbers from the real numbers, you just get rational numbers that remain there. Then rational numbers on the other side, irrational, remove the real numbers, you just remain with the empty set as well. So that will be union the empty set. Then this, yeah, the rational union empty, as set algebra, you know that it's just going to give you rational numbers. So this is how you get the symmetric difference of those sets, and this marks the end of our class.